Hello, welcome to Connected Conversations on Science Streams. I am happy to have a returning guest, Professor Matt Bellis from Siena College, to just talk physics and hang out. And so I've asked people to bring their questions because so many times I'm on here just talking physics and I don't have all the answers, believe it or not, even though I do happen to teach 8th grade physics. So we'd like to bring in some more notable experts than myself because there is a lot going on in physics as usual. So if you want to introduce yourself, Matt, and say a little bit about yourself for anyone that doesn't know you.
Thanks very much, Scott. Thanks for that introduction. So my name's Matt Bellis. I am a professor at Siena College, not from where Scott is, just outside of Albany, New York. And I'm also a member of the CMS collaboration. So the CMS experiment is one of the larger experiments at the Large Hadron Collider located at CERN in Switzerland. It actually straddles the Swiss and French border. I'm also, I don't know if I told you this or not, Scott, but in January, I started a position at Siena as the coordinator for our data science program because some of my work has been in data science and data science adjacent fields. And I have a lot of activities and interest in public outreach, other research with students, both interacting with the public as well as at different schools and stuff like that. So that's who I am. I also do not have all the answers to set the
That's part of the fun,
expectations.
though, right? Not
Right,
knowing the
right.
answers. If we knew it
True,
all,
true.
what would be the point of science?
It's the journey. It's figuring out the
Yep,
answers.
yep, yep. So it's cool to hear about a lot of your data science stuff. I remember during COVID, you were doing a lot of that data science piece as well. So that's kind of right. I think you were kind of going in that direction even then, as far as looking at data and that public outreach piece.
Yeah,
So that's
yeah,
pretty
yeah.
cool.
Yeah, I had started actually doing more with data science about 5 years ago, maybe 4 or 5 years ago. I started working with another faculty member and a group in Albany, a community group that applies for and then distributes funding to support homelessness in Eastern New York State. And much of the money that they get is from HUD. And so they're required to record data on the individuals and the families that receive some of the support. But nobody's really looked at the data to try to understand, is the money being used effectively? Are there ways that you could decrease recidivism, people who fall back into homelessness? And so that's been part of an ongoing project that's very different from the particle physics research that I do, and ideally has some sort of social impact. And then there have been a bunch of students that want to do sports analytics. That's a big thing. And then, as you said, during COVID, I actually wound up using a lot of the publicly available data as assignments, where we would take the raw data and just use it to make some plots and try to understand things about like rates of change of infection rates and stuff like that. So nothing like a really deep dive with the COVID data, but for many of the students, it was useful to kind of see like all the plots and charts that they would see on the news or social media, like where it was coming from and how to kind of like reproduce those plots themselves.
Awesome. Um, and and so this is kind of like an evolving, field that you're kind of getting into and working with students. And
That's right.
these are undergraduates as well.
These are all undergrads. That's exactly right. And then this past semester, for the first time, I actually worked with a student, a high school student down in Chatham, who I knew his mom was a teacher. They were looking for a science internship mentor. And so we did a little bit of data science. It was, for me, it was kind of like, well, how much could I teach? How much could I work with a high school student who had already taken some basic Python programming? That's a fantastic screen.
There
Um,
was a redemption. I know Eagle Scout was going to do it, so we have, we have to amuse him.
so we worked, again, he knew Python, so I taught him some of the more data science tools. We did some stuff with the COVID, and then I pointed it to some other data sets, and he was making plots of like locations of Chipotle's and like what states have the highest like Chipotle to individual like ratios and stuff like that, and kind of just like fun playing around with the data, that type of thing.
That's fine, and I think that's when you can start having fun with the data, I think
Right.
that's pretty cool. And that's when students realize the power of the data. And there's so much data out there. Um, and I think it's hard to impress upon even my students especially, but everyday people, how much data is just publicly available and out
That's
there.
right. That's right.
It's mind-boggling, and
Yes.
if you know how to get to it and analyze it, there's just publications waiting to happen, isn't there?
That's exactly right. That's exactly, and the hard part, one of the things we talk about in the data science classes, you still have to always be cognizant of where the data came from, right? And
Mhm.
how clean it is. So, there's a lot of data sets that get scrubbed, right? So they're cleaned up for public consumption. And so the person with the data set might be like, oh, I didn't collect all the information I needed on this person or this person, so I'll throw it out. Now, the question is, was there a systematic reason you were throwing out like groups of people or something like that? And does that start to bias your data? Siena has the SCRI, which runs a SRI, which is the Siena Research Institute, which runs these polls. And it's really hard to get a poll that's like a uniform sampling of a population. They ran into this years ago.
Mhm.
When they realized a lot of younger people did not have landlines, right? People were making the shift to cell phones. And so you might get a data set that's like, oh, here's all the people in our poll. And if it's all only people with landlines, for example, just suppose, if that's not information isn't in the data set, you could bias yourself. So one of the things we really talk about is the idea of like understanding your data so that if you make some inference based on that data, you can understand what the limitations of that inference are.
All right, you have your first physics question here,
Uh-oh. Okay.
and
What's it with
Dash is asking, and I don't know if this. He says, uh, I want to ask Matt if he believes in multiverses. All right, and is that a matter of belief or
So
faith or what?
it's a great question. So let's unpack your question for a second, right? So and then we'll get to like belief stuff, right? So let me get super nerdy for a second about like what
Please
is
do.
science, right? Right. So right. This is the community for it. So it's a real question, like what is science? 400 years ago scientists were natural philosophers, right? That was the terminology. And it was based on this idea of philosophers who were thinking about like the natural world. And then you have someone like Galileo who starts running like systematic experiments, and then Newton who's making these systematic observations. And instead of this idea that came from the Greeks about just like thinking about what the world is, and trying to like intuit everything by pure thought, people started running experiments. And then people started thinking about like, well, how is science different from philosophy, and are they different? And there was an influential philosopher of science, I want to say in the 1950s or 1960s, Karl Popper.
Mhm.
And he had this idea that science is anything that can be falsifiable. He's like, you can't always prove something that is true in like an infinite number of cases, but if you can come up with an experiment that would falsify your theory, that's science. And Karl Popper's idea, and this idea of falsifiability as the thing that distinguishes science from other, intellectual endeavors, really stuck around. Now, there's been quite a bit of criticism of Popper's ideas, and if that's too narrow, and a lot of it comes up in the context of thinking about things like the multiverse or string theory, and these ideas that are not testable by any means that we can conceive of now. But right, so the question is an idea like the multiverse forever untestable? Is it forever indistinguishable from other theories, or is it that just there's no way to test it right now? If there is never any way ever to test it, is it science? And at that point, then you might rely on something like faith or belief or something like that. Okay. So this is a long way of getting to the question. I missed the name of the person, but this is a fascinating question. I can't see the chat, so I don't know what's going on. I don't know if people are getting like impatient or anything like that. But um, earlier
Um,
this year, I was at a conference in Santa Barbara with a lot of theorists. I'm not a theorist; I'm an experimentalist, but I got to go to this conference because of people that I work with, and there was actually discussions about things like the multiverse. And the multiverse has different meanings to different people. There's the quantum idea of the multiverse, where every time nature has a choice to make a decision, you flip a coin, you cover it, the coin is either heads or tails. At the quantum
mhm.
level, when you open your hand to see it, there's a universe where it's heads and a universe where it's tails. But there's this other related idea of bubble universes where the laws of physics are fundamentally different than ours. And there's a certain appeal to that type of multiverse because it answers certain problems in physics. I think the idea of that type of multiverse really was out of vogue like 20 years ago, but there is a lot of really enthusiastic interest in exploring this idea, both of those ideas about multiverses, where you have this quantum mechanical branching of the multiverse. People say, like, oh, anything can happen. It doesn't mean anything can happen. It doesn't mean like there's a universe where I'm Doctor Strange or something. And then there's the idea of these bubble universes where within our universe, you might have this other region that is, hundreds of light years across, where the laws of physics, the constants of nature are very different. So these are really, really valid regions of experimentation. I find myself really starting to believe, I guess, for lack of a better word, or buy in the idea of these bubble universes where the laws of physics are very different. I used to not really think that that was actually that interesting to think about. And now, as I understand the problems that those might answer, I actually think that,
Mhm.
as much as I might say believe, yes, I think that type of like multiverse where there's other universes where the laws of nature are very different, I kind of feel like that kind of makes sense to me.
Okay. You're Bubbleverse curious. Uh,
Yes, yeah, yeah, that's right, that's right, that's right. I would like to learn more about these. Um, the quantum mechanical multiverse is so like that level of thinking about quantum mechanics is so deep to me that it's like this area that I don't even find myself thinking about much, not because I don't think it's interesting, but because it twists my head around so much that I have not been able to formulate a real kind of like preference for either things like, you know, multiverse branching and stuff like this, the many worlds interpretation. So I guess what I would say is I am multiverse agnostic. I am not opposed to the idea of this like quantum mechanical branching, but I don't think I understand it all enough to have a real like belief structure, if that makes sense.
okay. Uh, we do have some more questions. And Science Nephilim, thanks for stopping in along with everyone else. Next question, Michael asks, can you explain about particle physics in the simplest terms possible? So we have to put a limit on this. So simplest
Okay.
terms, maybe, I mean, 5 sentences, or should I make it 5 words? What? Let's do let's do both. You get five
Okay.
sentences, and then you get 5 words.
Okay. Particle physics tries to explain what stuff is, what things are at the lowest level. And then it tries to explain how that stuff talks to one another. Some people then try to explain how all of that at the smallest level gives rise to everything else. I'll stop there.
Okay, that was good. All right, good.
So I would say, so if I wanted to do like the Hemingway 6 word, story,
Yeah.
I would say, what is stuff and how does stuff talk to other stuff.
Okay.
I don't know
Okay.
if that was satisfying enough,
That
but
is
that
very
was
satisfying. I think that
okay.
works because it's one of those things where simplest terms. I think you kind of nailed it.
So,
All right. Next question. Can something go faster than the speed of light?
okay, great. Okay, so now let me
The
be the
classic
pedagogical.
question.
Right. So let me be the pedagogical teacher for a second. And I think Scott probably has an eye. As soon as I start talking, he'll know where I'm going with this. So first, I'm going to do the annoying teacher thing where I'm going to restate your question. Um, because of course things can travel faster than the speed of light, depending on what the light is moving through. So for example, the speed of light is slower in water than it is in air, and the speed of light is slower in air than it is in a vacuum. So this is related to a quantity of material objects called the index of refraction. It has to do with how electromagnetic radiation propagates through that medium, and it's influenced by the atoms and the molecules around it. And so light travels slower in water than it does in a vacuum, which means that you can have subatomic particles like high energy electrons that travel faster in water than light does in water. And when that happens, you get this effect called Cherenkov radiation. And it's analogous to a sonic boom, right? I can have an airplane that travels faster than the speed of sound. And when it does, it kind of like pushes all the air molecules into one another, right? They can't get out of the way fast enough. And you get this like big boom. And it is analogous to this idea of the electron is moving faster than the actual electromagnetic field that's radiating away from it. And you get these cones of blue light when a particle moves. And we actually use this in many of our particle physics experiments because you have some like transparent plastic material and a particle will go through it. And if you see that light, then you see that something is moving faster than the light, speed of light. But I don't think that that's actually what the question was asked. The question is really, does anything travel faster than the speed of light? Um, so the answer is no and yes. No, there is nothing that we know of that has mass. Like in the Einstein special theory of special relativity, basically that is a fundamental limit. You can't have anything um, moving faster than the speed of light if it is massless. So photons and gluons, it is basically required to move at the speed of light. And if it is heavier, then it moves slower than the speed of light. Now for the yes part. Einstein's general theory of relativity says that while objects cannot move faster than the speed of light, space and time can actually expand faster than the speed of light. And so, not talking about a photon and not talking about an electron, but if you had 2 points in space, Einstein's theory, general relativity, allows for those 2 points in space to separate faster than the speed of light. And we believe that this expansion of the universe actually happened very early in the universe, like microseconds after the Big Bang. It was a period called inflation. This theory of inflation explains a lot of cosmological observations. So it's kind of weird to wrap your mind around. Like a photon, an object cannot physically travel from one place to another faster than the speed of light, but the actual universe is allowed to, by the laws of physics, it can expand faster than the speed of light. And that's a weird thing to think about. I know. And it's taken me like 20 years to kind of wrap my mind around that.
Now, isn't it also the case, though I heard this once, to argue why things can travel, at least information can travel faster than the speed of light? If you have two
It
particles, like, and they're connected, then if you change the spin of one, you'll instantaneously change the spin of the other.
good. Okay. Great. Yes. Okay. Good. 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 So, right. So this idea like goes back to quantum mechanics. Great. Yeah. Fantastic, Sky. Called me out. Good. Good. Hold me accountable. So right, so there's this theory built into quantum mechanics called entanglement, and it's this thing that messed with Einstein's mind. This is what one of the things that Einstein had so much trouble with. You can create two particles in such a way, such that let's talk about this quantity called spin. And usually you can think about a spinning top. So if one particle is spinning clockwise, the other has to be spinning counterclockwise because they came from an object that was not spinning, right? So one's clockwise, one's counterclockwise. And we represent this as one is spinning with like an up arrow and one is spinning with a down arrow, saying like which way they're going. So quantum mechanics says that at the instant that they're created, neither one of them knows what they are, right? They are actually in a superposition. They are both, this one is both spin up and down, and this is both spin down and up. And they do not know what they are. And then, as you say, if you measure one of them, the other one instantly becomes spin down or the opposite. So if one of them is measured spin down, the other one instantly becomes spin up. This seems to violate that information travels faster than the speed of light. And here is where my real depth of understanding of quantum mechanics starts to break down. I'm going to explain to you the way I understand it. This has been measured experimentally, many times. There's a famous experiment that seeks to explore something called Bell's inequality, and this really is how we think the universe seems to work. The idea that instantly one of them becomes the opposite of the other. And it seems like information is being passed between the two of them. And if you wanted to make the argument that that information is being transferred faster than the speed of light, which it does seem to be, I could not argue otherwise. It is different, however, than the idea of me passing information to Scott,
Mhm.
right? That type of like randomness, like one of them is random and then the other is down, that does not allow me to actually transfer information to Scott faster than the speed of light or to anybody else. Because it's this probabilistic thing, I can't do something, right? As soon as I do something to one of those particles, I've broken their connection. All it means is
Okay.
that if I measure it as spin up, I know that Scott's going to measure it as spin down. But if I try to do something to disturb it in such a way to force it into a state, it breaks that entangled nature between them. And so it seems like, I think it does seem like information is passing between the particles, but it does not allow us, or as far as we know, any species to transmit information from one person to another.
Okay.
Is my understanding, my limited understanding.
That's okay. We That was really cool. So we have a lot of other, I think, very classic physics questions
Sure.
in here. And we're gonna try to get some of them do go together.
Okay.
Um, so uh, du- du- du. Is it possible to time travel? And my joke for my students is always, okay, just sit there for a moment. There you go.
me,
You're two
me
seconds into
too.
the future.
Me
Time
too. Me
travel.
too. Me too. Me too. Me
They're like,
too.
that's not what I meant, Mr. Biter. You
Right.
know what I meant. I'm like, did you want to wait longer?
Yeah. Yeah.
No,
Yeah.
then we can get into some other, stuff with
Sure.
it.
Sure.
But
Sure.
so that, and that kind of goes with, there are some questions about when it comes to time travel, messing with the space time, in like, I guess, like wormholing and things like
Yeah.
that
Yeah.
as
Yeah. Yeah.
well.
Right.
And then therefore what's inside the black hole. I think that was kind of like the thinking that went through
Right.
here. So we could go through an entire semester of physics right here. Um,
Oh my gosh.
but maybe I should force you to sum it up in 10 words.
Right. Maybe not 10 words, but this will probably be short because I
Okay.
don't, this
I
is
know
one
this
an
isn't
area
like,
that I'm less
right. This isn't quite where you're at. But
So, again, Einstein's equations allow for regions where my understanding is you can travel back in time. Now, when I say you, I mean like, like a particle or a group of particles. Theoretically, you could have these wormholes that allow space and time to be linked. And so, my understanding is that um, there are mathematical solutions which seem to imply that yes, you could have a particle that travels back in time. Those mathematical solutions require a quantity of something that seems to be defined as negative energy. We don't know if that's a physical thing. And so it's not clear that this is something that can happen. You mentioned inside a black hole. And so, Scott, when you teach or have learned or done anything with physics, you usually have like position on the y axis and time on the x axis. And then you can say where something is, like you draw this plot and like you have a line or a curve or something that's moving in such a way that it's position versus time. And one of the things that I remember learning about when I took general relativity in grad school, I don't really understand this, is that inside a black hole, space and time, those axes get flipped somehow. And I don't really know what that means, but somehow space and time are defined differently inside the event horizon of a black hole. Um, like once you pass the Schwarzschild radius. I don't really know what that means, but this idea that kind of time gets redefined has always like kind of like blown my mind a little bit.
Mhm.
And if I was to write like a science fiction story, black holes are fantastic, fertile ground for these types of things. And, I would probably build that into it somehow.
So when my students are graphing speed, it's not that they got the axes wrong. They were just thinking in terms of black holes. How very
They were so
prescient of them. That
advanced.
wow.
Good for them.
Yeah.
That's right. That's right.
Jeez.
That's right. They're ready for grad school.
Right.
So that's why I wish I had a more satisfying answer, but that's as
No,
much as
that's good. You got a lot of people thinking in chat. So,
good, good.
um, here's a fun question. Do the laws of physics always exist?
Fantastic question. Okay. Great question. So, there's a kind of simple, boring answer, and then there's the mind-blowing answer. And even the simple answer is mind-blowing, right? So, one question, if I could take that question and slightly rephrase it, is are the laws of physics always the same? And there have been a number of studies and tests that have tried to understand is if the speed of light was different, a 5 billion years ago, how would that manifest itself? And I've heard people try to explain things like dark energy, which is this idea that the universe is not just getting bigger, but it's actually getting bigger faster, it's expanding. I've heard people try to explain dark energy and this idea that the speed of light has actually changed over time. And then there are these quantities that we measure that are basically like the strength of electromagnetism or the strength of like how nuclear decays happen. And there is a region in Gabon, Africa, where 2 billion years ago there was a self-sustaining nuclear reaction. So when nuclear plants run, if you have the uranium too close to each other, all of these neutrons come out and they just like burn through it, and you either get a big explosion or it just like burns and burns and burns. It gets hot and like basically runs out of all the fissile material pretty quickly. And so you have to have these rods and something that will like slow the neutrons down, so that they can like, because if the neutrons are moving too fast, they actually go past each other and they don't burn at all, that you don't get the nuclear reaction. So you need something to slow. It's called a moderator, and you can either use water or you could use like carbon for it. And in this region of Africa, there was like these kind of perfect conditions of clay and wet clay, which acted as a moderator, and then enough plutonium that they believe over about 100,000 years, you had this self sustaining nuclear reaction, which is crazy on its own. What is equally amazing to me is that people have studied this reaction and the isotopes that are left behind to try to understand if the laws of physics were different 2 billion years ago, that you could actually maybe infer that 2 billion years ago, the strength of certain physics constants were actually slightly different. Now, there's obviously, right? Right. So the the error bars, the uncertainty on that is obvious, is very, very big. And so there's been nothing definitive shown, but it's an area of research to whether or not these constants are actually constant. Now, the other part of the question is related to what I said before about this idea that there are regions of our universe where they're like these bubble universes, and the laws of physics are totally different. Maybe there's no strong nuclear interaction. Maybe the speed of light is 10 meters per second. Maybe, I don't know, time and space are different. Maybe there's 12 dimensions. And this is a way to understand why our universe is the way it is. It's not that we're special. It's just that there are like a Googleplex of universes out there. And so you're likely to find one that happens to be like ours, in which case there are all these different universes with different, physical laws. So that to me kind of actually is appealing in some way, this idea that we're not special, we're just one of like a Googleplex of things, and the laws of nature, the laws of physics are really different in all of those. So again, for your students, if there are any students listening, if you like get something wrong on a test, you could be like, I was actually talking about a different universe. You can't mark me wrong. You didn't say what the laws of physics were in this universe. I was thinking about this other bubble universe, a quadrillion light years away. So anyways,
You can
that would
try
be
that.
my
Wrong.
wrong, wrong, wrong. This universe is always implied in every question.
Yep. And it's also interesting. Not only would there be different universes with different physics, but you're saying maybe even in our own universe, the physics might have been different.
It
Right.
might have been different at different points in time.
Even just slightly. You just don't know.
That's right. That's right. That's right. And I think, we all do our experiments assuming that they're always the same. And we do our experiments assuming that if I built a Large Hadron Collider in the Andromeda galaxy, it would run the same way. But these are assumptions that, we haven't tested. I can't go back and run my experiments 10 billion years ago. The question is, if I observe stars that existed 10 billion years ago, are there observations I might be able to make, which would let me know whether or not the laws of nature were different?
Mm-hmm. Yeah, that's really, really, it is really interesting. And so I'm seeing a lot of questions, but we've already answered a lot of these questions, just slightly different. Like, is it possible to travel in the fourth dimension? Well, the fourth dimension's time.
Right.
We already talked
But
about that.
I think they probably mean like the fourth spatial dimension, right?
Okay. Well, okay. Space. They didn't specify which dimension.
Oh, okay. Yeah. Right. Right.
So you could discuss that if you want, all the different
Well, I'll say
dimensions,
this.
and especially
Yeah.
if you want to get into the string theory and the idea of multiple dimensions, and a lot of, I think physics now is kind of relying on this idea of multiple dimensions to explain phenomena.
That's right. That's right. So string theory kind of requires that the universe is 10 dimensions, but we only observe 3 of them because the other 7 are it's 10 spatial dimensions. The other 7 are incredibly small. They're on a scale, and the picture is like, my pen is actually 3 dimensions, but if I was like really, really far away from my pen, it would look one dimension. It would look like a one-dimensional line. That's the canonical picture, because our brains can't really think about that. And so if that's the case, it's not clear that there's any way physically, we can travel in those other dimensions. It might be that the atoms in my body do extend into those dimensions. And again, if I was to write some science fiction, I would probably use that as a way to think about like teleportation or something through these other dimensions. But right now, we don't even know that they exist. So to my mind, there's no real research in that type of teleportation or stuff like that.
Yep. Here's an idea. I got into this about a month ago. I was reading an article on like sound and not photons but phonons, and it's a virtual particle.
Yes.
And there's a lot of research going into this kind of thing, even though it is completely made up, but it works out mathematically.
Okay.
Right? Because
I want to know what you mean by I want to hear,
meaning
like,
a phonon doesn't, there's not a sound particle like there is a light particle. Right.
That's right. That's right. That's
so,
right.
and
There's like
that's what I mean by it's
energy,
virtual. But
yeah.
it works thinking of it as a real thing. And so the question here was thoughts on virtual particles.
Right. So okay. So there's 2 things. So let me kind of comment on what you talked about for a second, and then I think I know what they might mean by virtual particles. So have you ever heard of a soliton?
A soliton? No.
Yeah. So a
I don't think so.
soliton is again one of these kind of like related to the idea of phonons. It's a vibration that kind of acts like a particle, and you can think of
Hmm.
it as traveling from one part of a solid to another in the way that a phonon, right? A phonon is like some sort of like quantized unit of vibrational energy that kind of like moves around, right? It's very localized. It's like a particle. It's not an electron. You're absolutely right. It's not an atom. It's not a proton, but it's like a vibrational amount that's here, and then a vibrational amount that's here, and a vibrational amount that's here. And because it's so constrained to one region, you can think of it as like a particle. Now, solitons, which is again this idea of like kind of like a wave that acts like a particle, were first observed in canals, and I think it was like in England or Wales. And it's this very um, specific set of circumstances where if the canal is a certain size and you create a wave of a certain size, that wave will travel for like miles without dissipating. And it's just one wave, it's just one wave, and it just moves along, and if I didn't know anything better, I'd be like, "Oh my gosh, look at that thing that is moving through." And again, it's not a particle, but it is this very localized amount of like energy that doesn't dissipate. And that I think is related to this idea of photons where yeah, they can like you can have this particle thing that moves through, but it's like a localized amount of energy. And you're right, that is a very, very active field of study. People use phonons to like make measurements of different materials. Now, the virtual particles, I think, if the person might be referring to, is this idea that in the vacuum of space, there are these particles that are created for very short periods of time, like matter and antimatter, and they're created for very short periods of time, and then they wink out of existence. They return to the vacuum. And the more massive they are, the shorter that they exist for. And these virtual particles appear in many of our equations, right? They appear kind of like what you said, they're imaginary. We don't really, you can do all the calculations without believing that they exist, but we need them for the mathematics. And it goes back to this idea in quantum mechanics. If something can happen, it does, but you've got to calculate the probability. So these virtual particles are needed for our equations. However, there is this effect called the Casimir effect, which seems to imply that these virtual particles are actually real and not just imaginary. And the effect is like this. If I have two metal plates like this, because particles can also be waves, you can think about the waves that you can like kind of fit between these two plates. And then there are waves and particles outside of the plates. But as you get the plates closer and closer together, there is actually fewer virtual particles that can exist between them. And so, because there are more of these virtual particles on the outside, they actually exert a pressure which can be measured. And so, people have done experiments, and it's CASIMIR. And if anybody looks up the Casimir effect, they will find these studies that have been done that seem to show that these virtual particles, which are like this like bubbling, ghost particles of the vacuum, seem to be like real and they exert an effect. And then there are these other experiments that we do in particle physics where you can show that they're having an effect on like these really kind of esoteric, like they're called deep scattering experiments that kind of get through this like kind of virtual ghost protection of particles around stuff. Like I'm being very loosey
Mhm.
goosey with my imagery, but an electron is surrounded by these virtual particles. And if I have another electron come in, the first thing it sees is these virtual particles before scattering off. If it's got enough energy, it actually penetrates through this barrier and you can measure that effect. But the Casimir effect is the thing that like blows me away. That's like, oh my gosh, this is like a real thing.
Even though it shouldn't be a real thing.
Right. It at first it's like this is just a math. This is just an artifact of the math. I draw these loops and I do these things, and then it's like, oh, I can measure this like pressure from these like virtual particles.
Right. And another question, which is right up your line of what I want to get into talking about, is what happens when you cut particles in half? But you guys don't actually cut them in half, you smash them in half.
We smash them and we right. That's right. So we smash them And then, right, so we smash them together, and usually instead of cutting things in half, we're actually sticking them together. We get something bigger, but then that thing breaks apart and decays. And as far as we know, it decays into like the smallest things we know. So we don't try to cut them up anymore. The limits of our instrumentation and measuring suggest that the electron is a mathematical point. It is mathematically consistent with the idea that it cannot be cut up anymore. And then there are particles like quarks, which can't exist on their own, but also seem to be mathematical points and stuff. Now, that's different from talking about the wavelength of them, which has a certain size. Um, but uh, but yeah, we don't actually cut them up, but we do allow them to break apart into as small as they want to break up into.
Um,
And then we try to put them back together
and see what else comes out of it.
and see what else comes out.
Why doesn't the electron fall into the nucleus of the atom?
Great question. Oh my gosh. I remember thinking about this back in middle school, high school and stuff like that. Um so let me give you a handful of answers and stuff like that. Um no, I'm just going to jump to the answer. It does. The electron totally exists in the nucleus of the atom at some very small period of time probability. So let me explain what I mean. We have this picture, right? And I am as guilty of it. It's going to sound like I'm criticizing, the educational system, but I'm not. But like, everybody knows this picture of the atom, that looks like this. There's the nucleus and the electron. It's what Dr. Manhattan drew on his forehead for any Watchmen fans out there. And that's the Bohr pick model of the atom. And that Bohr model is fundamentally wrong. And so if you kind of think about this, it does look like the electron is orbiting and that it should eventually spiral in. At the time, this picture was understood by the idea that the electron could only give up discrete amount of energy. And so because it went around and it was like one perfect wavelength around, it existed at the region of one wavelength. It basically was just the right orbit to basically for that wave to come around and eat its own tail, and it would be stable. And the only way it could like fall into the nucleus was by giving up energy. And actually, that was kind of like an open question. Why didn't it give up that last unit of energy? But this is the wrong picture. And so, this picture, the easiest, what you want to do is you want to divorce yourself of this picture because this picture does look like it should totally fall in because the electron actually does fall in. Because our picture is that we have our nucleus and then the electron exists in some sort of cloud around it. And if you solve Schrodinger's equations, you find that there are some regions where the electron prefers to be and some regions where the electron doesn't. So this is a very, very poor rendition where the darker regions are where the electron prefers to be, not the nucleus, but these regions out here. And these lighter regions are regions where the electron might be found because it's just a probability, but it's less likely. And here's the thing. When you work this out, you find that the electron has a non-zero probability of being in the nucleus. Now, just because it's in the nucleus, right. And I actually give the students this problem, when they work it out, like what overlap of the wave function is in the nucleus. Because if it's in the nucleus, that's okay. Nothing has to happen. However,
something can happen.
And the thing that can happen sometimes is something called electron capture. So if the electron can be in the nucleus, there is a probability that it can interact with a proton in such a way that you wind up getting a neutron and an antineutrino that comes out. And this is a radioactive decay process called electron capture. And because one of your protons turns into a neutron, it actually changes the atomic number. It happens, it doesn't happen in every atom. Like it doesn't happen in hydrogen, or it's like so incredibly rare that it's never been observed in hydrogen. But there are other. So I think like gallium has some isotopes where the inner shell electrons do sometimes get captured by the nucleus. When that happens, you have a hole in your inner shell electrons, which then gets filled by other electrons that kind of like cascade and fall down. And what you observe are the X rays that come out of it because of these electrons kind of like falling in from one level to the other. And and then you can use this to then calculate, well, what's the probability of the n equals 2 electrons of getting captured? And you find that it all agrees perfectly with like theory. And it all agrees with this theory of these like kind of like fuzzy pictures where, yes, the electron can exist inside the nucleus.
There you go.
There you go.
You've heard
Right?
it.
Still blows me
Which
away.
is cool. Now this gets to some of my questions. I shared an article with you, and I'll put it in chat. We talked about this before,
How do I get to chat?
where
Oh, there it is. Is that chat? Sorry,
where they were weighing the boson at Fermilab, and it didn't come out the way they expected.
okay, yes. Oh, there it is. There's your
Right.
there's the
And
yeah.
one, I know that you had spent some time at Fermilab as well as at CERN. So it one of the things that always surprises me is the level of precision that physicists can get when measuring almost
Yes.
anything at this point, right? It's
Yes.
just
Yeah, yeah, yeah,
ridiculous.
yeah. Yes.
So is it really that surprising that they found something different when you're getting to that level? Or is it really, I know this was like the really high sigma, so it's a really different,
Yeah, so
result. I mean, did it really break
well,
physics?
okay, right. So if they are correct,
Mhm.
I don't know if I don't know that I would say if it broke physics, but a lot of things have to be re-examined, and it could
Mhm.
very much point the way to new physics. The question right now kind of goes back to what you said, and I'll take what you said and rephrase it. I think the question a lot of people have is, did they measure this that precisely? And a lot of people have a lot of respect for the individuals that did this work. I think everybody knows that they're not only, it's not just that they're smart people, but they understood that experiment really well. And the work that they did was really well done. So I've seen now like a couple of talks given by the scientists that did this. And just to give you a sense of, right, so for background, for people that might not be as familiar with this, there is a fundamental particle called the W boson. The W boson is a mass about 80 times that of the proton. It was discovered in the 1980s. It was predicted in the 1960s, and it's believed to be the particle that mediates a fundamental force called the weak nuclear interaction. And what that means is that this is the particle that allows like radioactivity to occur. So every radioactive reaction, from uranium to like the potassium in a banana, this happens because of a particle called the W boson. And what physicists are able to do is they take this fundamental quantity called the weak coupling, and they also take this quantity that's related to the mass, that is the mass of the W boson. And with these two quantities together, you can calculate the probability of many of these radioactive decays happening. And it's not just the radioactive decays, there's a bunch of other they're called weak decays. These different reactions occur that rely on, again, this quantity called the weak coupling and something called the CKM matrix, which are kind of really fundamental, and then the mass of the W. And so, because these are really fundamental quantities, it's been really important to measure the mass of the W. Measuring the mass of the W is really hard. And that's because when it decays, it almost always produces, as one of the particles it decays to, a neutrino, which we never measure. A neutrino is incredibly light. it does not interact with any of our particle physics experiments. You have to design a special dedicated experiment to measure it. And so it leaves the detector and we have to infer its existence. Or the W decays to sprays of particles called jets, which are, a bunch of pions, bunch of muons here, a bunch of stuff, bunch of photons. And those are also really hard to reconstruct precisely. The experiment that Scott's referring to that made this ran at Fermilab, probably on the order of 20 years or so. It collected data. It was one of two experiments at a collider called the Tevatron. This was the experiment that discovered the top quark that led to a Nobel Prize. That's the heaviest particle. It was the first one to get up to a tera electron volts of collision energy. It actually ran at 2 tera electron volts. But when the LHC came on, the LHC was exceeding many of the design parameters of those experiments. And so in 2011, the experiment shut down and stopped taking data. However, a core group of scientists kept analyzing the data and kept making improvements. We have new computers, we have new understandings of some of the background processes. And so they were able to take this and improve not just their background measurements, but they redid something called the alignment of their these chambers where there's these wires that are strung. So one of the ways they make the measurements, like Scott's talking about, these incredibly precise measurements, is you have to tell where the particles went. And so you stretch these wires in a region where there's gas. A charged particle goes through. It ionizes the gas. The gas drifts to these wires, these sense wires, and you read out the signal. It's really important to know exactly where that wire is. And I mean down to like as close to like the micron level that you get. Previously, when they were running the experiment, they had, and it's not just going in there with like a ruler to figure out where things are. You basically figure out where they are. And then you say, well, I've got cosmic rays coming down from the sky. I turn off my magnet so the cosmic rays are going straight. And then you can, in software, kind of infer exactly these locations of the wires. And once you know the wires really precisely, you get to measure all these other quantities of your, particle physics collisions really precisely. And one of the things it seems like they really improved on was their location, their knowledge of the location of these wires with some new studies. And I think I'm probably misstating it, but I think before they knew the location of the wires down to like hundreds of microns. And I think now they're down to tens of microns, or they like knew it to a millimeter and now they're down to hundreds of microns. But it's on the order of like a factor of 10 improvement, I think, in the positions. And this is where, they get to this level of precision that says we are now in disagreement with every other measurement that's been made. And we are in disagreement with our understanding of the standard model, because you can infer the mass of the W measurement from all these, of the W mass from all these other things. Okay. So nobody doubts that these individuals did an amazing job. And yet, you talk to people and they're just like, I know they didn't make any obvious mistakes. And they're also like, there's no way they got to this level of precision. Like this type of collider, this type of experiment, this is like really, really hard to do. And everybody's like, I don't know what they did wrong, but I don't believe that their level of uncertainty is as small as it is. And when you get to things like uncertainty, you're kind of relying on a lot of other stuff. Okay, so what could be happening here? I do think that there are a couple of studies that they could do which would double check things. Some people say that they've done them, and maybe I just haven't found the right publication that says that they've done them. But I think there are a couple of studies that they could do to kind of give people a little bit more confidence in some of their like alignment, these calibration studies. So I'm just going to put it out there that they've probably done them and I just not have read it. That's my mea culpa. There's another kind of out for physics, that's not that physics is broken. And that's that there is a fundamental difference between the Tevatron collider at Fermilab and the experiments in Europe. At the in the LHC, the Large Hadron Collider, we collide bunches of protons and bunches of protons. At the Tevatron at Fermilab, they collided bunches of protons with bunches of antiprotons. Now, matter and antimatter are believed to be at a certain level exactly the same except for the electric charge. But when you collide protons and antiprotons, the way that the W particles are produced is slightly different than the way they're produced when you have protons and protons. It doesn't mean that the W particles are different. It means that their production is different in such a way that they're produced in such a way that's different, that they might have slightly different momentum characteristics or the quarks that produce them. You're more sensitive to the motions of the quarks in such a way that it actually introduces a different uncertainty. And so I believe that there are people that are now doing calculations and trying to do studies to see if the fact that one of them was doing proton antiproton and the other was doing proton proton, do we have certain assumptions about the precision of our knowledge that are, that those assumptions are false, that our understanding of those two are different enough that it could be like, oh, yeah, when you measure the W in this process, you get this value with these assumptions. When you measure it in this way with these same assumptions, you get a slightly different value. And the thing is that our assumptions are actually not correct. And that would bring those more into agreement.
Right. So basically, more research is needed.
More research. And so the LHC experiments are really, I know within CMS,
Mhm.
we're really working hard to measure the W, but if it's
Right.
different, there are still kind of like ways that you could say, well, it's not really new physics. It's this other aspect of our ignorance about something at a really fundamental level.
Right. And that gets into kind of the next, one of the things I want to talk about are what are the new things in this run at the LHC that we're kind of hoping to find that we might get at this new level of energies?
Right. So great question. So the last when we took data between 2016 and 2018, we ran at 13 TeV center of mass energies. The LHC just ran recently at 13.6. We would like to get up to 14 TeV. It does get you a little bit more energy to potentially create new particles, but I don't know that we'll actually see something new because of the energy.
Mhm.
What we are supposed to be doing, though, is running under conditions such that we will, over the next, I think, 3 to 5 years, will collect about 10 times more data. And collecting more data allows us to do much more precision measurements. And there are a handful of experiments that have been done over the last 3 or 4 years that suggest that there are what we refer to as tensions between different measurements, right? You would expect them to be exactly the same, but they're kind of different, but their error bars are also kind of big. And so if you could shrink the error bars, you would see that before, when the error bars overlapped, you couldn't tell if they were different, but now you shrink them and you're like, oh, these are different.
Hmm.
And one of the big things people are looking at is something called lepton universality. We kind of assume in many of our theories that if something decays to an electron, it will decay in exactly the same way to a muon, which is related to the electron, or another particle called the tau. But the last few years have seen experiments which seem to hint that it's actually slightly different. And that would very much be a sign of new physics. And there are a bunch of different theories out there that every theorist has their pet theory. They would be like, my theory can explain lepton universality, different or violation of lepton universality. So I think there's actually going to be quite a bit of work once we get, like, again, 10 times more data than we have to really do these precision measurements and test things like lepton universality.
Wow.
That's one of the things I think people are really going to be like looking at. And the way to test this is with a whole suite of different experiments and different measurements. So there's not going to be one smoking gun. It's going to be a whole like suite of experiments that kind of all start to converge on the idea that things are really more different than we thought.
And that's exciting.
Very exciting. Very
I mean, if
exciting.
you get the same stuff, I mean, you're not learning anything.
No, that's right. And we are forging into like really uncharted waters in terms of like the precision, and we might find that things are the same. In which case, that's actually kind of interesting because we know there are, this idea of things like dark matter and dark energy, which don't fit into the standard model. So if we don't see anything here, it starts to throw open a wide range of like, wow, this really is the Wild West. What is all of this stuff? And maybe we come up with like totally different paradigms of how to think about this.
At what point do we give up on dark matter?
Right. So like always, I will rephrase the question. Right. A better thing to ask is when do we give up on the idea of dark matter as being a particle of within a certain mass range?
Mhm.
And I think that there are a lot of people who have given up on this idea. There was a long time where people predicted the mass of dark matter to be between 10 and 100 times the mass of the proton. And I think for the most part, that's mostly out the door. There are now a lot of new theories thinking of dark matter as being such a light particle that it actually acts more like a wave. And that is a pretty active area of research of how we could actually detect that. And that might be not by looking just in our particle physics experiments, but looking at how stars are distributed in the galaxy could be something. So so I don't think we give up on the idea of that there is something extra contributing to the gravitational field, but I think the idea of dark matter as being like one of these 10 times the mass of a proton particles, I think that that is there are very few people really pushing on that.
Wasn't it the case that when the neutrino was first discovered, they thought that the neutrino was kind of like dark matter that would account for a lot of those physics, but
Right.
it turned out that it wasn't as massive as they thought and as many of them as they thought, or something like that.
Yeah, so there you're right. So the neutrino was discovered before there was this real concrete idea of dark matter, but then later on people were like, "Oh, maybe it could be neutrinos." The problem with neutrinos is that they move really fast, which means that they
Hmm.
move faster than the escape velocity of the galaxy. We believe our current theories of the evolution of the universe is that dark matter clumped together first.
Hmm.
And the dark matter then pulled in regular matter in order to make galaxies. So the dark matter kind of provided a seed location for the galaxies to form. And because neutrinos are moving so fast, they can't become gravitationally bound to pull anything else. There is an outstanding theory of something called a sterile neutrino, which is much heavier and could be a dark matter candidate. And that is still an open, fertile field of discussion and research.
Awesome. Well, chat, here is your chance, your last gasp of questions um, for Matt. So if you have anything, we've been chatting for a little bit over an hour now, so we will entertain some last questions before we wrap things up.
Has it really been an hour? Like, it seems
Yeah.
to go wow.
Yep, it has. So
Oh, I totally
very
believe you.
cool.
I know some of my answers become, like, super long and rambling. It's hard to be sometimes concise about these things, which I kind of don't always understand fully. So often when I'm talking to you, I'm thinking through the process myself.
Yep. Well, Maddie Holmes, yes, streams go fast. Um,
Did
yes.
you know that there are, in the galaxy, there's a galactic, concept called streams? These are when a smaller galaxy has been like ripped apart and is being
Hmm.
pulled into a larger galaxy. And so people talk about the streams of stars. There's something called the Sagittarius stream, which was actually discovered in part by Heidi Newberg at RPI. And so you have people that are looking for new streams in our Milky Way, which would be these like
Hmm.
old fossil galaxies which got pulled into and ripped apart by our galaxy.
Wow.
Anyways, if you Google galaxy streams, you'll see that.
Yeah, I don't think I had heard of that particular term before. That's really cool.
A lot of good science out there.
Oh yeah. So thanks everyone for hanging out tonight, and thank you, Matt. And I'll hopefully see you
Thanks for
next
having
week.
me.
If I when I
This was a
stop by
blast.
Siena, I'll be I'll
I will see
hopefully
on Thursday, right? Career for Jam.
yep,
I'll see you there.
yep. I'll be there with my my eighth graders as I
Awesome,
try
awesome.
to get them excited about careers in STEM.
I'll
Um,
talk you up to them.
I'll talk you up to them.
Thank you very much.
And so, but I'm excited about that. Get out of school.
Very cool.
And Science Nephilim said it was wonderful. Thank you.
Thank you, everybody, for joining. Thanks for
and
these
before I
questions. These are
go,
great questions.
Yeah, you guys had wonderful questions.
Oh, yeah.
Make sure I spelled that right. Give a shout out to Science Nephilim there.
Nice. Thank you, Science Nephilim. So Nephilim, those were Nephilim the offspring of angels and humans? Is that what the Nephilim were? Like from the Old Testament, like old Apocrypha or something like that? Or am I totally, is that how Nephilim is spelled?
You said, yes, biblical times.
Biblical
Exactly
time,
right.
yeah.
You got it.
Okay, cool. Nice.
Expert in on the Bible as well as physics.
No, just they popped up in some book that I read at some point. I'm not an expert on the Bible.
Your brain went there.
There you
go. Awesome.
Cool.
All right. Well, we are going to sign out. We're gonna stop by and raid Rocket Sage. She's only been streaming for an hour, so she's probably still gonna be on for a bit. Says they're talking about volcanoes. So from one science stream to another,
awesome.
We will hop over there.
Cool.
So make sure that you hang out and check out all the other great science streamers that are out there sharing the love of science. And thank you again, Matt, for being here. And
thank you. You're welcome, and thank you very much. Thank you.
Let's get this raid going. And so please hang out for that raid. Say hi to Rocket Sage, and I'll be back streaming something on Friday. I'm not sure yet. I'm not sure, but that's the goal. All right. See everybody.
Bye, Scott. Thanks, everyone.
All right.
Oh my gosh. EJ, hi! And Science Streams. Hi guys. Hi Maddie. Hi Ernok. My summer car. Wait, what's this about? What's my summer car about? Please tell me. So much volcano. My science. Science Streams. Hi Michael. Hi Fondle. Nowhere. Oh my god. Ryan, thank you for gifting a sub to Science Streams. It's a racing survival game? Do you have a clip you want to share? I'd like to see this. Welcome, lovely humans! We are talking about geothermal energy right now and the various countries and their outputs. The USA is in the lead with 2.5. However, that being said, the US is a much, much bigger country than some of these other countries that are producing quite a bit as well. We have a very excellent